starting from a number of base unit operations, and configure the robot, both the deck and the arms, to have a type of capabilities appropriate for different types of applications. It can be configured to do, in addition to liquid dispense, we can do viscous liquid dispense, we can do slurry dispense, powder dispense, pellet dispense. So we can really handle a wide variety of different types of materials in terms of preparing different types of samples. It can enable a variety of different types of sample processing from a wide range of thermal treatments, covering a wide range of temperatures, different types of mixing, shaking and vortexing on the deck. The ability of doing filtration and extraction. In particular, I'll talk about this in the context of the crystallization workflow. We have a unique and proprietary way of doing filtration, a heated seal filtration that allows us to generate a series of saturated solutions, transfer those and filter those at temperature from a sealed vessel into a sealed vessel, so you don't need to worry about evaporation. And what you're left with is a filtered, saturated solution that you can then use to generate crystals, the subsequent crystallization processes. We have the ability of doing coating and making coatings, of doing capping and sealing, as well as a variety of other types of things, including centrifugation, other types of processes as well. We also integrate a variety of different types of analysis on deck. So these could be things like mass with an analytical balance, pH, viscosity, imaging, on-deck injection into an LC, and even such things as friction and conductivity. All this is wrapped with some of our software, which I'll talk about in a bit. And it really is a very open architecture, allowing us to be modular, be able to add capabilities over time as well. On the right side, I show a picture of the core module itself. The module you're looking at there is 1 meter left to right, so sized to fit on a bench or sit inside a fume hood or an enclosure. And at the bottom right, it shows a bird's eye view, a top view of what a typical deck layout would be for crystallization, where we have a variety of different heated, cooled, stirred zones on the deck. Each zone is able to hold a number of microtiter sized plates, and with wash stations as well. And the arms in this particular case have either a single tip, so it has a heated tip, so it has a piercing tip that can pierce through a septum, aspirate up fluid into a heated zone, keep saturated solutions hot and solubilized as they're transferring fluid around. The other arm has a 4-tip piercing tip of the heated zone for transferring fluids. The other key platform that we actually have is our informatics to enable scientific workflows. This is a software platform we refer to as our Laboratory Execution and Analysis Software, LEA. And this is really designed to do the design, execute, and analyze and report, as it indicates down the left-hand side. There's a series of different software packages to enable each of these. We have an array-based experimental design package. We call it Library Studio. It allows a scientist to design arrays of experiments. Within that environment, it's very much like an Excel for chemists. Within that environment, one can bring in and set up a variety of different types of source materials, whether it's powders or solutions or different types of materials. One can create a variety of different virtual stock solutions. And one can also set up and plan a variety of different experimental parameters. It could be temperature, cooling rates, pressures, stir rates, reaction, cooling times, crystallization times, a whole variety of parameters. One then can create different arrays. What's shown here in the screenshots in the upper center is an array of it's a 6x8 array, a 2x4 array, so a variety of different types of formats can be created. And one can then create a sequential recipe of how materials are added, what the order of addition is, what types of parameters there are, and really be able to capture a recipe to create and process various libraries. Once it's created and a user can then view the composition space that one is going to explore and share that with a team, the software enables one to save that to a database, and it creates a unique identifier. And that library identifier then lives with the library through the whole rest of the process and allows the rest of the data to be tied together. This is all some activity that scientists can do at their desk. They can do it remote from the lab. So when they're in the lab, there's another piece of software, which is shown here in yellow, that really allows one to do control of the various types of laboratory equipment. They use it to control the Symix robotics. They also use it to control other pieces of robotics, other pieces of lab instrumentation, or the analytics. This software allows one to load up a recipe, so it goes into the database, pulls up the recipe, it reads the recipe, and then it will create the library following the recipe based on the library identifier that is read by the barcode. It can then do the crystallization, it then follow all the processes for those, creating a set of samples that will then go on to the different analysis stations. We'll talk about that in a bit, but the way that when you go to different stations, whether it's a HPLC, a microscopy station, or a Raman station, or an X-ray station, one simply takes a set of samples there, scans in a barcode, and analyzes the samples. The samples then, the data is all captured, and each data from each of those stations is then saved back to the database relative to all the design information that was stored originally. When the scientist has been back at their desk, they're able to use a final piece of software, that we refer to as PolyView, to give enterprise access to both the raw data and the summary data, be able to visualize all the data, and be able to generate reports. The nice thing about doing things in this way, where you've got the design and the reporting separated out, is, and this is, even though this particular slide talks about protein formulation, this is actually true for crystallization as well, we're able to have a very distributed way of doing research. We can have people doing the experimental design in a separate location from where the actual crystallization or the actual formulation development occurs. So in the center of the slide, we show a map of the world with a number of different yellow dots. Each of those yellow dots could be a different research or technical center for a particular company, and it is certainly possible where you could have a set of scientists in one yellow dot designing experiments and submitting experiments to be done. The experiments can be conducted at another location, and this is actually, we actually do this work where the experiments are actually conducted in California, and the data is then pushed back out so that the data can be analyzed back at the client's or the customer's labs using software that's been deployed to their lab as well. Okay, so I'm going to spend some time today talking about pre-formulation in particular, really looking to a space where we're looking to do lead compound characterization to identify various forms of an API, really with an eye to try to find optimal druggable properties and protect intellectual property. We're covering crystallization, and it's quite broad. People do polymorph studies where you're looking to find different polymorphic and different crystal forms of a given chemical entity. These are typically done with different solvents, different concentrations, different solvent concentrations, and we do the analysis based on birefringence, Raman, X-ray, and LC. We also do salt selections using a very similar variation of the workflow. In this case, you pair your API with different types of counterions and look for a crystallizable or an optimal drug form, and it may be something that is either crystalline, where the free base is not. It could be something with improved solubility or improved stability of the actual crystalline form. Finally, we're also able to do co-crystallization studies. This is where you're crystallizing the API with something other than actually a specific counterion, where you're actually getting actual proton exchange. So you're not forming a true salt, but you are co-crystallizing your API with something else, again, to get typically better crystallization properties, better bioavailability properties, better solubility properties, that type of thing.